Hello everybody. In our last class, we discussed about the relationship in between the raw moments and central moments, and we deduced the mean of different discrete and continuous distributions. Today, we shall discuss about some results related to kth moment and one more concept that we shall introduce over here is the idea of variance and standard deviation. So let's start with this result. It says that if two real numbers are there, say A and B, these are two real numbers, then for these two real numbers, the if you consider this kind of random variable ax plus b, say y is equal to, suppose ax plus b is a random variable, then its kth derivative, not derivative, then its kth moment, mu k of this random variable ax plus b, that would be is equal to a to the power of k multiplied by the kth moment of the random variable x. All right. Uh, Particularly if this A is a positive quantity, then this A is called the measure of scale, and B is called the position of origin. How is it possible? Suppose if you want to represent any random variable with suppose with the unit centimeter. Hmm. Suppose it is a measure of certain length and x has the unit centimeter. And suppose y is another random variable measuring the same distance. That distance is to be represented in terms of millimeter. Okay. Then from the value of x, you can generate the value of y, a centimeter to millimeter conversion. Okay, then x is written in terms of centimeter. Whenever the value of x, this value is multiplied by a constant quantity. Suppose when it is multiplied by 10, okay, when 5 centimeter is multiplied by 10, you will get the result in terms of millimeters. Got it? So that is the idea, that this a, whenever this x, this random variable x is multiplied by a constant a, it represents the change of scale. That means maybe from centimeter scale to millimeter scale, maybe lower scale to higher scale, or higher scale to lower scale, depending upon the value of this constant. Okay, sometimes we divide the random variable x by by a number a. In that case, you see this x by a, this kind of expression, this x by a, this x by a as can be considered as equal to x multiplied by 1 by a. Okay, so whatever it is, a multiplication of x by a constant a, or division by x by a constant a, it means we are just changing the scale. All right. Therefore, multiplication of a random variable by a constant means we are changing the scale. Again, if we add or subtract some real number from the variable, from this kind of random variable, like x is equal to, suppose y minus some constant a, or plus some constant a. In that case, what does it mean? It means that we are just changing the origin. Plus or minus of some constant means we are just changing the origin. And what this does, this result says, the result says that over here the right hand side expression is dependent only on the quantity small a. Got it? Therefore, we can say that it is actually dependent on the scale of measurement. The real number small a actually represents the scale of measurement, and the real number small b would represent the position of origin. As because there is no expression involving small b on the right hand side, therefore we can say that the that the right hand side expression does not dependent on the origin. So we can say that the right hand side expression is independent of the choice of origin. Got it? Or the central moments are independent of the choice of origin, but it depends upon the scale of measurement. That means upon the value of small a. So this result can be geometrically interpreted in this way that the central moments are independent of the choice of origin, but it depends on the scale of measurement. Hmm. The proof is relatively easy. What we do over here, we assume that y is equal to this kind of y, random variable y is equal to ax plus b, where a and b are two real numbers. Then mean of y, we denote it by m suffix y, mean of y or expectation of y. That would be is equal to expectation of ax plus b. That is equal to a into expectation of x plus expectation of b. Expectation of a constant is equal to the constant itself. Therefore, we can simply write b over here. And that becomes is equal to a into expectation of x means and the mean of x. So we write m of x in place of expectation of x. So a into mx plus b. So we get this type of result. So this is the relation that my is equal to a into mx plus b. All right. Then what would be the kth moment of y? Kth moment would be defined in this way: y minus my whole to the power of k, its expectation. Y minus my whole to the power of k, its expectation. All right. And we just put the expression of y over here. What is y? Y is equal to ax plus b. So we put the expression of y and we put the expression of my. Already we have computed the value of my. My is equal to a into mx plus b. So ultimately minus b would come, and this negative of b and this positive of b, they would cancel each other. This b and this b will cancel each other. Okay. So in this way, only we shall have the expression ax minus a into mx whole to the power of k. And from this expression, you can take a to the power of m outside this expectation. Sorry, a to the power of k outside this expectation. So ultimately, the expression within this bracket, that would be x minus m whole to the power of k, its expectation. That is actually the kth moment of x. So we can write the expression as equal to a to the power of k multiplied by mu k of the random variable x. So this is the proof that mu of ax plus b, this mu k of ax plus b, this expression is equal to a to the power of k multiplied by kth moment, kth central moment of x, mu k of x. So that was the proof. And particularly if a is greater than 0, then we get the change of scale, and b refers to the change of origin. So what I told you earlier, that the result is independent of the change of origin, but it depends upon the change of scale. Got it? That is the final conclusion we have from this result. Next, we apply this result, we apply this theorem and we get this corollary. You see, if we consider this kind of random variable, y is equal to x minus its mean m divided by sigma. What is sigma? That we shall consider later on. But for this normal distribution, suppose we already have two parameters, m and sigma. This is another parameter, normal m sigma parameter. Now we already got the interpretation of m. We already proved the result that m is actually the mean of the normal distribution. And today we shall again we shall also get the interpretation of sigma. But for the time being, we consider normal m sigma distribution. Suppose x is a normal m sigma variate, and we define this kind of expression: y is equal to x minus m divided by sigma. And then this expression can be written as 1 by sigma into x minus m by sigma. And we again now apply the previous result. Then what we can do, we can say that m of y is equal to what would be 1 by sigma, this 1 by sigma into m of x minus this constant quantity, minus this constant quantity m by sigma. And you see over here, what is mx? This mean of x, the mean of the random variable x. The x, this x is actually a normal m sigma distribution. So m is the mean of the random variable x. Therefore, in place of this mx, okay, in place of this mx, we can put small m over here. Clear? So in place of mx, we can put small m. Then ultimately, the total value of this my, mean of y, this mean of y becomes is equal to 0. And this kind of random variable, you see, y is equal to x minus m by sigma. We proved the result that y is equal to x minus m by sigma is actually a standard. It follows the standard normal distribution, and we already got this result that in case of standard normal distribution, the mean of that distribution is equal to 0. So this is a different kind of verification of that result, that mean of this kind of standard normal variate is actually 0. So these results are to be used in as an objective question. All right. Now we have a result, a very important result for normal distribution. Over here, this kth order central moment, is represented in terms of lower order central moment. Got it? All right. So let's first prove this result, and we have a second part of this theorem. The second part says that show that the central moment of odd order. All right. That means when k is an odd positive integer, central moment of odd order, these kind of central moments, all these central moments vanish. All right. So we have to show that all the central moments of odd order vanish in the normal m sigma distribution. Clear? We are going to prove this result. We are going to prove the first result, and as a consequence, we will be able to prove this second result. Okay. Now over here, you see this is the density function of standard. This is the density function of normal in m sigma distribution. You see we have a printing mistake over here, not np. It should be normal m sigma distribution. Okay, normal m comma sigma distribution. So we suppose that x is a normal m comma sigma variate, and in that case this fx would be this kind of expression 1 by root over of twice by sigma e to the power of minus half into x minus m by sigma whole square, and the spectrum is from minus infinity to infinity. Sigma is a positive number and m is any real number in between minus infinity and infinity. Sigma and m are the parameters of the normal distribution. Okay, and we all know that mean of the normal distribution is actually is equal to m. And remember, if sufficient marks are given, you will have to prove this result that mean of the normal m sigma variate is equal to m. Got it? Over here already I have proved this result in my previous lecture, so I am skipping that proof. Hmm. So over here, the kth central moment mu k, this kth central moment mu k is equal to expectation of x minus m whole to the power of k. And in terms of the integral formula, we can write it as integral from minus infinity to infinity x minus m whole to the power of k f of x dx. Okay. And you see over here, if we consider if we put the expression of fx, this would be the expression of fx 1 by root over twice by sigma e to the power of minus half x minus m by sigma whole square. You see over here, if you consider this expression, only this much expression within this bracket, suppose if you consider only this much expression, in that case you cannot directly integrate this expression e to the power of minus you cannot directly integrate this expression e to the power of minus half x minus m by sigma whole square. In order to integrate it, you need the support of one factor x minus sigma multiplied by this dx. Got it? Hmm. And that's why I have separately kept a factor x minus m so that we can ultimately, if you consider this total expression, then total expression can be integrated. And in order to integrate it, we apply a transformation. We apply this kind of transformation that x minus m divided by sigma is equal to z. Got it? We apply this kind of transformation, x minus m by sigma is equal to z. So after taking this kind of transformation, you see this expression becomes a bit easier. This exponent becomes e to the power of minus half z square by 2, and in that case x minus m would be is equal to simply z sigma. This x minus m would be is equal to z sigma, and this dx would be is equal to sigma dz. So we are applying this kind of transformation over here. And now you see this is actually an infinite integral, so I am trying to represent this infinite integral in terms of the limit. We can consider two arbitrary numbers, capital A and capital B, in between which we can integrate this expression in this integrand, and after that we can take the limit. You see I made one more mistake over here. A should be negative of infinity and B should be positive of infinity. A should be negative. This A should be negative of infinity. A should tend to negative of infinity and B should tend to positive of infinity. So these are a few mistakes that I have done. So please be a bit careful whenever you go through this file. Anyway, so let's continue over here. So if we suppose that limit a tending to minus infinity and b tending to infinity, in that case you see the correspondingly in terms of z, the lower and upper limit will be changed in this fashion, and take the limit a tending to infinity and b tending to minus infinity throughout this integral process. Now you see over here we can consider this expression, this quantity as the second factor and this quantity as the first factor. We are going to integrate it by parts. Okay. So you see this is easy to integrate. So that's why this factor has been taken as the second factor. Second function, and then we perform the integration by parts. So first function is kept constant, integral of second function, and next over here in the next term, this is the derivative. This is actually the derivative of the first function, this much. Z to the power of k minus a has been kept fixed, then k minus 1 into z to the power of k minus 1 is the derivative of this first function. And after that this is actually the integral of the second function. Now if we put the limit a tending to minus infinity and b tending to plus infinity, in that case by repeated application of L'Hopital's rule, we will be able to find that this upper and lower limit, after taking the upper and lower limit, the value of the entire expression becomes is equal to 0. Got it? The value of the entire expression becomes is equal to 0 by repeated application of L'Hopital's rule. And therefore effectively only the contribution from the second integral will take place. Okay, only the contribution from the second integral will take place, and after taking the limit a tending to minus infinity and b tending to plus infinity, you see this expression, whenever again we are trying to express this expression in terms of x, just by putting z is equal to x minus m by sigma, what we observe is that we have x minus m to the power of k minus 2. We started with with this mu k. So we initially had the expression of x minus m whole to the power of k in the first line, but now we have x minus m whole to the power of k minus 1, and this is actually the expression of the density function of the normal m sigma variate. Got it? So we can express this integral in this way: x minus m to the power of k minus 2 multiplied by fx dx, and that is actually the expression of k minus 2 order moment mu k minus 1, central moment mu k minus 2, k minus second order moment mu k minus 2, the central moment. So we have proved the first result, that mu k is equal to sigma square multiplied by k minus 1 into mu k minus 2. So this is the proof of this first part. Now in this second part, you see, in this second part we already observed that the difference between k and this p index is k minus 2. So if k is an odd integer, if this k is an odd integer, then this k minus 2, this would also be an odd integer. Okay. And so if we consider mu k is equal to 3 over here, if you will have mu 3, and over here we will have mu 1. Now, what is mu1? Mu1 means expectation of x minus m, and we all know that mu1 is always equal to 0 for any random variable. So, if we put k is equal to 3, you observe that this mu3 would also be equal to 0 because of the fact that mu1 is equal to 0. Got it? So over here, what we are doing, we are just trying to replace this k, trying to replace this k by an odd positive integer. In this relation number 2, we are trying to replace this k by an odd positive integer. Then we shall have this type of expression. You see, mu suffix twice n plus 1, that should be is equal to, by putting k is equal to twice n in this relation, we will have twice n into sigma square into mu suffix twice n minus 1. And you see, similarly we have, if we want to find out mu twice n minus 1, then we will have mu twice n minus 1, that is 2 into n minus 1 into sigma square into mu twice n minus 3, and so on. So finally we shall have this type of result: mu 3 is equal to 2 into sigma square into mu 1. Now you see, mu 1 is equal to 0, so mu 3 is equal to 0, and similarly its previous first odd order moment, that is mu 5, then mu 7, and so on. All these odd order moments are equal to 0. In fact, if we multiply all these results, then what we observe, that mu twice n plus 1 can be written in terms of mu 1. Got it? Mu twice n minus 1 can be written in terms of mu 1, and as because this mu 1 is equal to 0, therefore all these odd order central moments, will be equal to 0. So this proves that in case of normal m sigma distribution, all the odd order central moments are equal to 0. And later on we will prove that for a symmetric distribution about mean, you see the normal distribution, if you consider the density curve of the normal distribution, the density curve of the normal distribution looks like this. Say this is the real axis, and over here about the point mean, about the point m, this density curve looks like this. Not This is not a very good sketch. The density curve looks like this, symmetric about the mean, about the point m. And due to symmetry, one can prove that in case of any symmetric distribution, the odd order central moments are all equal to 0. In case of symmetric distribution about the point m, all the odd order central moments are equal to 0. We can prove all these results later on in this subsequent lectures. Okay, next, one more important result that has been selected many times in exam, that says that the existence of higher order moment implies the existence of lower order moments. Maybe central moment, maybe any other kind of moment. So we consider general case, that we consider any moment about a point, maybe about a real number a. We are going to show that this kth moment, existence of this kth moment, implies that the lower order moment of order k minus 1, suppose, this moment exists. Expectation of x minus a to the power of k, if this expectation exists, then expectation of x minus a to the power of k minus 1, this moment also exists. And of course over here k should be greater than or is equal to 2, because if k is equal to 2, the smallest value, then over here k minus 1 would be is equal to 1. So over here k should be greater than is equal to 2, and this small a is any real number. Small a is any real number. It may be the mean value or it may be some other kind of real constant. And the proof is actually divided into two parts. So we shall prove an inequality, this kind of inequality, modulus of x to the power of k minus 1, that is less than is equal to modulus of x to the power of k plus 1 for all real number x and k greater than is equal to 2. So we are going to prove this result at first. In case 1, we study this one in the following two cases. One is the case number 1. Over here we suppose that modulus of x is less than 1. If modulus of x is less than 1, then you see x to the power of k minus 1 minus x to the power of k. In this expression we can take x to the power of k minus 1 common. Within the bracket we have 1 minus modulus of x, and as because 1 minus modulus of x is actually a quantity which is smaller than 1. You see modulus of x, if modulus of x has the value 0.5, 0.7, if modulus of x has the value 0.7, then 1 minus modulus of x will have the value 0.3. Got it? So in any case we can say that 1 minus modulus of x, this expression within bracket, is always less than 1. And as because modulus of x is strictly less than 1, so we can say that altogether the right hand side quantity over here x to the power of k minus 1 is also less than 1, and 1 minus modulus of x, this is also less than 1. So altogether the total quantity is less than 1. Therefore we got the result, we got this result, that if we now replace this expression, if we just put this expression on the right hand side, shift this expression on the right hand side, then what we get? We get that this x to the power of k minus 1, this is less than x to the power of k plus 1. This was the result that I am trying to prove at first. So we proved this result when modulus of x is less than 1. Now we consider the second case where modulus of x is greater than is equal to 1. If modulus of x is greater than is equal to 1, then we evaluate this ratio x to the power of k minus 1 divided by x to the power of k plus 1. We compute this ratio. You see, we can multiply the numerator by modulus of x to the power, simply we multiply this numerator by modulus of x only. We multiply the numerator by modulus of x and divide this expression by modulus of x. Then on the numerator you shall have x to the power of k divided by x to the power of k plus 1, this kind of expression. And there this x to the power of k divided by x to the power of k plus 1, this expression is of course less than or is equal to 1. And therefore we can say this expression is less than is equal to 1. Therefore effectively on this total expression is less than is equal to 1 by modulus of x. And as because modulus of x is greater than is equal to 1, therefore 1 by modulus of x, its inverse, should be less than or is equal to 1. And what we finally get, that this left hand side is less than is equal to 1. So if we cross multiply and shift this expression on this right hand side, the denominator, if we just shift this denominator by cross multiplication on the right hand side, then we get this result that x to the power of k minus 1 is less than is equal to x to the power of k plus 1. So in any case, whether you consider case number 1 or case number 2, we observe that this inequality is always true. So whether modulus of x is less than 1 or greater than or is equal to 1, it doesn't matter. This inequality is always true. X to the power of k minus 1, modulus of x to the power of k minus 1 is less than is equal to x to the power of k plus 1 for all value of x, and k greater than is equal to 2. Okay. And now we replace this x over here. You see this x was any arbitrary real number. This result is true for all the real number x. So if we replace this real number x by x minus a, even then the corresponding result should be true. So this is the corresponding result where we replace x in this relation by x minus a. Got it? So we get this type of relation number 4. Okay, small a is a real constant. Now you see, if you consider a discrete distribution, we are proving this result for discrete distribution. For continuous distribution, the result is very similar. So if we consider a discrete distribution, the distribution of a discrete random variable, then suppose xi is the spectrum and fi is the probability mass function. Then over here in this relation number 4, this relation is also true for any arbitrary real number x, and therefore we can put xi is equal to x in this relation. Xi is equal to x is equal to xi in this relation number 4 over here. And after putting this expression x is equal to xi, and then afterwards we multiply what after putting x is equal to xi, we get this type of relation xi. And after that we multiply this expression by f. Got it? Then on the left we will have fi, fi, and this one will now become simply fi. So this should also be the quantity fi. Okay, that means we will have this type of result. You see, x minus I xi minus a whole to the power of k minus 1 multiplied by fi, that is less than is equal to xi minus a whole to the power of k into fi plus this mass function fi. So we are actually multiplying by fi. After putting x is equal to xi in the relation number 2, we are just multiplying by fi. So we get this type of relation number 5. And now take the summation. If you take the summation over here, you see you will get this kind of summation I varying from minus infinity to plus infinity. Then we get this kind of summation over here. And we shall get one more summation over here. And we know that this kind of summation from I is equal to minus infinity to infinity fi, this summation, this total value is equal to 1. So we can say that the summation, this kind of summation of fi, this summation is actually a finite quantity. This last term in equation number 5, after taking summation, the corresponding expression would be a finite number. All right. Now we are given that expectation of x minus k to the x minus a whole to the power of k. This expectation exists. What does it mean? It means that summation xi minus k. Okay, summation xi minus a whole to the power of k. This kind of summation whole to the power of k multiplied by fi. Multiplied by this fi, this kind of expression where summation is taken from I is equal to minus infinity to plus infinity. This kind of summation should be convergent, not only or convergent, it should be absolutely convergent. Absolute convergence means over here we shall have to consider the absolute series, the modulus. And as because this fi is a positive quantity, this corresponding absolute series would be written in this form: modulus of xi minus a to the power of k and multiplied by modulus of fi. But fi is actually the probability mass function, and probability mass function is always greater than is equal to 0. So we can remove that modulus from this fi, around this fi. And then we will have this kind of series. So this series is absolutely convergent. It means that this series is also convergent. And therefore by comparison test of real numbers, we can say that this left hand side expression, this series is also convergent. This series is a convergent quantity. What does it mean? It means that the lower order expectation, this x minus a to the power of k minus 1, the order is k minus 1, this lower order expectation exists. Got it? This lower order expectation exists. This much we can say. The lower order expectation exists. Okay. And so we finally get this proof that whenever the higher order expectation exists, this lower order expectation also exists. The existence of higher order expectation implies the existence of lower order expectation. So next, let's start the idea of variance. Let's introduce the idea of variance. What is variance? Variance is actually the second central moment. The second central moment, expectation of x minus m whole square. This is called the variance of the random variable x. And it is denoted by VAR. VAR of x. Sometimes it is also denoted by mu2. Mu2, that is actually the second central moment. This is actually called the variance of x. Okay, variance of x. And what is the meaning of this variance? You see over here, if we express this expectation of x minus m whole square, this expression, expectation of x minus m whole square, this expression would be represented in terms of discrete random variable as modulus of xi minus m whole square into fi, summation I varying from minus infinity to infinity. Okay, and over here you see this is a square quantity, modulus of xi minus m whole square. So in place of this square we can write simply modulus of xi minus m. In place of simply xi minus m whole square, we can write it xi minus m whole square, modulus of xi minus m whole square. Got it? And what is this? This can, you see, this can be interpreted in this way. Suppose the probability mass is distributed on the real axis or on a single axis, where this is suppose minus infinity and this is suppose plus infinity. The probability mass is distributed along this line. And suppose in somewhere over here in the middle, suppose this is our mean value small m. On the left and right, the probability mass is distributed as per the spectrum on the left and right. Now suppose this is the position of xi. This is the position of xi. All right, this is the position of xi, and then this much difference, this much distance, xi minus m, or if the xi is situated on the left side, if xi is situated over here, then we shall have this kind of distance m minus xi. So m minus xi or xi minus m together, they can be represented as modulus of xi minus m in this way. Modulus of xi minus m, its whole square multiplied by fi. So what does it mean? We can say that this expression, this modulus of xi minus m, this is actually the distance. I deleted this picture. The distance of the mean value m, distance of this mean value m and xi. So we can say that this is actually the measure of how much distance xi, how these xi are distributed. If xi are situated far away from this mean value, then the value of this xi minus m whole square, this value will get increased. Got it? Again, I am saying that if xi are situated far away from m, either in right side or in left side, whatever direction you consider, if xi are situated far away from m, in that case the corresponding contribution that would come, and in that case this difference xi minus m whole square, it would be larger and larger quantity. Got it? But if the quantity xi is situated very close to the value of m, then this difference would be a smaller quantity, or in other words, variance of x would be a smaller quantity. So the larger value of this variance will imply that there are certain points which are situated far away from m. Or you can say that probability mass, these probability mass are concentrated on this zone and on this zone, that far away from m. and we have less number of distributed points in this M over here. And you see, if this value of x is larger, then we can say that there are certain points xi very large, at a very large distance from the value of m. Hmm. And if the variance of this x is a smaller quantity, then we can say that there is no such large contribution. That means xi, the value of xi are not present over here. Then what would be the value of xi? We can say that xi are concentrated near about the point m. Got it? Xi are concentrated near about the point m. This character is called the dispersion character. In technical language, we call it the dispersion property. Dispersion means how widely the xi are distributed about the point m, about the mean value m. Got it? That's why this variance is called the measure of dispersion. Let me introduce one more idea, that is called the idea of standard deviation. You see, suppose x is measured in terms of certain unit. Maybe that is the, suppose x is measuring some length. Then it may be represented in terms of centimeter or meter or millimeter, whatever unit you consider. And for the sake of discussion, I'm considering it in terms of centimeter. Then you see, x minus m whole square, that should be written m. You see, m is the mean, so m is the mean value, that should also be written in terms of centimeter. And therefore x minus m, this difference, that should also be represented in terms of centimeter. And therefore its square should be represented in terms of the centimeter square. And so in this expectation of x minus m, means this kind of expression I told you earlier. This expectation of x minus m means this kind of expression. So this x minus m whole square, its unit is centimeter square. All right, its unit is centimeter square. And what is probability? Probability does not have any unit. It is actually a pure number. So whenever centimeter square is multiplied by a pure number, and afterwards we are taking the summation, you see variance of x will have the unit as centimeter square. So what I am trying to say is that variance will be represented in square unit. Whatever be the unit of x, variance will be represented in terms of square unit. That's why we seek a quantity or measure of dispersion that would be represented in the same unit as that of the random variable x. So we expect that if x is represented in terms of centimeter, corresponding measure of dispersion should also be represented in terms of centimeter. And keeping this idea in our mind, we consider the positive square root of this variance. Got it? We consider the positive square root of this variance. You see this expression within this square root symbol, that is actually the expression of variance. We consider the positive square root of this variance, and that is called the standard deviation. This is again a measure of deviation, but the variance was measured in centimeter square. So whenever we take this kind of square root sign, ultimately the total unit will be now converted into the unit of the random variable capital X. Got it? So if x is represented in terms of centimeter, then this expression would also be represented in terms of centimeter. And you see over here, variance is equal to this kind of expression. So we consider this kind of quantity, root over of this kind of square quantity. And what is this? This is actually sometimes called root mean square deviation. Why root mean square deviation? Because you see standard deviation. Standard deviation is actually the positive square root, and it is actually represented in this fashion: sigma of x. This is also called root mean square deviation. Why? Because root represents this kind of expression root, and this expression, this is actually a kind of expectation. That's why we call it mean or mean value. Got it? This is actually the expectation of x minus m whole square. All right, that's why we call it mean value. So root mean square deviation. Why is it square deviation? Because we have a square quantity x minus m whole square. And why it is deviation? Because it is actually a measure of deviation, as I told you earlier, measure of dispersion or measure of deviation, how widely the probability mass is distributed about the mean value. Okay, that's why this kind of expression, the standard deviation, is also sometimes called the root mean square deviation, or the its a simple standard name is the standard deviation of the random variable x. Okay, so that is actually the idea behind proposing this kind of this kind of one more measure, the standard deviation. And one can prove this result that if x minus m whole square is greater than is equal to 0, then along with if the variance is equal to 0, then we can prove that x has the only one value, x is equal to m. Okay, and I am leaving this result as a homework for you. I have demonstrated everything over here. This is also an important result, that the second moment of a random variable about any point is minimum when taken about mean. That means second moment means the moment of x minus a whole square. Got it? Expectation of maybe not moment, rather second moment, that means expectation of x minus m whole square. If you consider the expectation of this kind of result, expectation of x minus m whole square, we have proved over here that this expectation would be smaller, the minimum, whenever this a is equal to m. Got it? We can prove that this expectation, the expectation of x minus a whole square, is the minimum whenever a is equal to m. And by computation, just we have proved that this kind of expectation of x minus a whole square is actually greater than is equal to x minus expectation of x minus m whole square, and this equality holds only when a is equal to m. That's why we can say that minimum value of left hand side, minimum value of this kind of expectation is actually occurs whenever a becomes is equal to m. Over here you see, in place of a we have the mean value m. That's why we say that this kind of minimum value of expectation of x minus a whole square arises when a becomes is equal to the mean value of the distribution m. All right. And in order to prove or in order to compute the standard deviation of different distributions, we have to use two results. One is that sigma square is equal to alpha 2 minus n square. I proved this result earlier. It is an easy direct proof that sigma square is actually the central moment, that is actually our mu 2. We already proved this result in the previous lecture, that mu 2 is equal to alpha 2 minus m square. So this is actually the same proof I have written over here. So I am skipping this proof. Okay. And we use one more result, that sigma square is equal to expectation of x minus x into x minus 1 minus m into m minus 1. And you see these two results can be selected as a short question of 2 marks in exam. All right, sigma square is equal to expectation of x minus x into x minus 1 minus m into m minus 1. That is actually a matter of one line. Sigma square, this x minus m whole square, if we represent it in binomially expand it in this way, and after that you just adjust x into x minus 1. In place of x square, this x square is now adjusted x into x minus 1, and afterwards one more x has been added over here in order to balance the x. And then you take the expectation over here, expectation of x is equal to m has been put, and after computation it becomes is equal to simply expectation of x into x minus 1 minus m into m minus 1. So sigma square can be written in this way. And in the computation of standard deviation of different distributions, we shall use either this formula or this formula according to our convenience. Okay, Sometimes we shall use this first formula, sometimes we shall use this second formula, these two formula as the working formula for computation of standard deviation. Over here I am leaving this result for you. You see, variance of ax plus b, that should be is equal to a square into variance of x, because already I have proved that variance of ak, if we put k is equal to 2, mu 2 is equal to mu 2 of this kind of expression, mu 2 of ax plus b. I have proved this result today as the first result. Mu 2 of ax plus b, that should be is equal to a square. That should be a square into mu 2 of x. Alright, so I proved this result today as the first result, and from this result we can directly prove this result. So I'm skipping this result. And if you consider the square root of this first result, you will get this second result. Variance means standard deviation. Variance, so taking square root, you will get this standard deviation. So sigma, small sigma refers to the standard deviation. So I am skipping the proof of this result as well. Okay. Now let's discuss the variance of standard deviation of binomial distribution. You see, already we have proved in the last lecture that m is equal to expectation of x, that is equal to np in case of binomial distribution. And now we are going to apply the standard deviation by this kind of formula. We are going to compute the variance of x is equal to expectation of x into x minus 1 minus m into m minus 1. Got it? So we require to compute this expectation of x into x minus 1. And what is the value of this expectation? Let's compute the expectation of x into x minus 1. That would be, theoretically speaking, I varying from minus infinity to infinity, xi into xi minus 1. Just in place of x, x, we are putting xi. Whenever we have x, we are putting xi. Got it? So xi into xi minus 1 multiplied by the mass function fi. Now, what is xi? In case of binomial distribution, xi is equal to I. So we just put I into I minus 1 over here, and this is the expression of a5. This is the expression of a5. And whenever we put the expression of a5, we find that I is varying from 0 to n. So now this theoretical range from minus infinity to infinity, now it converts into this kind of range, I varying from 0 to this upper limit n. Got it? I varying from 0 to n. Okay. Now you observe over here, if you put I is equal to 0, then this total term would be is equal to 0. Even if you put I is equal to 1, even then this total term would be is equal to 0. That's why if we put I is equal to 0 and 1, we get first two terms is equal to 0 and 0. And for the sake of simplicity, I have just considered 1 minus p is equal to q, just for the sake of simplicity of this computation. And afterwards, what we do, we observe that this NCI will be decomposed in this way: factorial of n divided by factorial of I into factorial of n minus I. And in this factorial of I, we have two factors. One is I, another is I minus 1. So we can cancel them, these two factors, and remaining we'll have this factorial of I minus 2. And in order to adjust, we are just extracting factorial of n and factorial of n minus 1 from this factorial of n. Then we shall have factorial of n minus 2, this kind of expression, factorial of n minus 2. Got it? Therefore, what we have, we actually have this kind of relation. If we take this n into n minus 1 outside this summation symbol, we are writing over here as n into n minus 1. And to adjust this result, we are extracting these two factors. You see, we have p to the power of I. So in order to adjust, we are just extracting p square out of this summation, and you see we will have p to the power of I minus 2. Okay, we will have p to the power of I minus 2 over here, and this n minus I has been written in this way: n minus 2 minus I minus 2. Therefore, this expression, this total expression can be written in this way: summation I is equal to 2 to n minus 2 c I minus 2 p to the power of I minus 2, then q to the power of n minus 2 minus I minus 2. And that is actually, if we just now take this kind of transformation, k is equal to I minus 2, then this would become equal to in summation k varying from 0 to n minus 2, n minus 2 ck p to the power of I minus 2 into q to the power of n minus, sorry, over here this p to the power of I minus 2, this actually will be replaced by p to the power of k, p to the power of k into q to the power of n minus 2 minus k. Okay, and that is actually the binomial expansion of p plus q to the power of n minus 2 here. And as because p plus q is equal to 1, so this value of this total binomial expansion, the value of this total binomial expansion would be is equal to 1. And therefore we actually have the final result is equal to n into n minus 1 into p square. All right, so ultimately we have this type of result, that expectation of x minus x into x minus 1 is equal to this kind of relation, that n into n minus 1 into p square. Okay, and we already know the mean value of in case of binomial distribution, so we can put m is equal to n into p, and after computation we get that variance of x becomes is equal to npq, or np into 1 minus p. Got it? Therefore standard deviation should be the positive square root of npq. This is the standard deviation of binomial distribution. Okay, and in case of Poisson distribution as well, we first find the expectation of x into x minus 1. And I am not showing the detailed computation over here. You can go through this computation by using the file later on. So in this computation, what we find that again this kind of expression, expectation of x into x minus 1 becomes is equal to mu square, and by this formula, a variance of x is equal to expectation of x into x minus 1 minus m into n minus 1. This value becomes is equal to mu. You see, we proved in the previous lecture that mu is actually was equal to the mean, or m, the mean value of the Poisson variate. So mu over here has another interpretation. We find that m, this mu is actually also can be written as the variance of that of a Poisson distributed random variable x. So mu, this parameter of the Poisson distribution, has two different interpretations. It can be considered as the mean value of the distribution, and it can also be considered as the variance of the distribution. So Poisson distribution is a particular case of the well-known, all these well-known distributions for which the mean value and the standard deviation, the variance, mean value and variance, both of these two quantities become same. And standard deviation would be is equal to sigma by root over of mu. All right. Now you see, I am leaving this deduction for Pascal distribution or negative binomial distribution for you. Over here, you see, you can find the expectation of x into x minus 1. Okay, you can find the expectation of x into x minus 1 in over here, and after computation you will find that this expectation of x into x minus 1 is equal to this kind of expression, q square r into r plus 1 by p square. And just if you put this expression in this working formula, we all know that m is equal to rq by p. So over here we can put the expression of m, and after computation we get the variance of the Pascal distribution, and therefore from that we can compute the standard deviation of that Pascal distribution. And in this Pascal distribution particularly, if we put r is equal to 1, then you will get this geometric distribution. So by putting r is equal to 1 in this geometric distribution and the same kind of computation, you will be able to compute the standard deviation and the variance and the standard deviation of the corresponding distribution. And you see, in case of normal distribution, you can go through this portion, this fx. This is the density function of fx, and in this computation of variance of x, we are just directly applying this formula, expectation of x minus mx whole square. And what is mx? Mx is nothing but is equal to the parameter m. So mx is nothing but is equal to the parameter m. Therefore, we can directly write x minus m whole square into fx dx. And just it is a very easy result just by considering this type of result, this type of transformation. Z is equal to x minus m divided by 2 root over of 2. You see, by this kind of transformation, we will be able to convert this variance of x into this kind of expression, z square into e to the power of minus z square dz. And this is an even function, so in this kind of minus infinity to plus infinity, this kind of range, we can convert it into 2 times of the integral from 0 to infinity. And afterwards we can put z square is equal to t, or z is equal to plus of root over of t. Then it is very good to see that the total integral is now converted into gamma function, gamma 3 by 2. And we know gamma 3 by 2 is equal to half gamma half. And what is gamma half? Gamma half is equal to root over of pi. So this root over of pi will get cancelled, and ultimately we will get that variance of x is equal to sigma square. Okay. So over here the standard deviation would be positive square root of this quantity. So positive square root of sigma square, that is actually simply sigma. So standard deviation for standard deviation for normal distribution is actually sigma. Sigma has the interpretation that it represents the standard deviation of the normal distribution. And in case of gamma distribution, we can apply this formula. This variance of x is equal to expectation of x square minus m. Expectation of x square, what is this? You can directly compute the expectation of x square. It is an easy result. So ultimately, you will find that expectation of x square is equal to L into L plus 1. So if we directly put this result, expectation of x square is equal to L into L minus 1, you will find that variance of x is equal to L. Variance of x is equal to L. And therefore the standard deviation of x is equal to root over of I. So these are the few standard results, and I am keeping this deduction for beta 1 distribution and beta 2 distribution as a homework. You can go through this computation. You would get that this we are applying expectation of we are computing expectation of x square, and afterwards we are just simply computing this variance of x by this kind of formula, and then from that result we can compute the standard deviation of x. And similarly, in case of beta 2 distribution as well, we can compute the variance of x in this way, variance of x over here, and we can compute the standard deviation. But remember, in case of variance, you see over here, in case of beta distribution, m should be greater than 2. If m is less than 2, then the variance does not exist, because in all this computational process, m is always assumed to be greater than 2. Otherwise, this gamma m minus 2 would not exist, and correspondingly expectation of x square would not exist, and so variance of x would not exist. Okay, so m should be greater than 2 in order to get the variance of x. If m is less than 2, then variance of x for beta 2 distribution, it does not exist. Okay, and for Cauchy distribution, we already proved that the mean of that Cauchy distribution does not exist, and therefore the higher order moment, we already proved that if the higher order moment exists, then the lower order moment exists. It is confirmed. And so we can say that if the lower order moment does not exist, then the higher order moment does not exist. In the converse result, over here the mean of the Cauchy distribution, we already proved in the last lecture that mean of the Cauchy distribution does not exist, and therefore its higher order moment, that is actually the variance, does not exist, and as a result the standard deviation does not exist. Okay, so these are some deduction related to variance and standard deviation of different standard well-known distributions.